we are ready to transition to our next panel. This is the Getting Gear on the Surface panel, and I will turn it over to Adam Schlesinger.
Yep, thank you very much. Yeah, really happy to be here today. I'm the CLPS, which is Commercial Lunar Payload Services Manager at NASA, and we have a great team of panelists that I'll introduce here in a bit. For anyone that's not familiar with CLPS, NASA is partnering with commercial providers to deliver enabling science and technology to various locations on the lunar surface. And as part of that effort, we're hoping to, one, build the foundations of a sustainable lunar economy, but also, with that science and technology, help enable future lunar exploration and be extensible to other destinations as well. So it's a newer type of model that NASA is exploring, and it's also important to remember that we're really in the early innings still for CLPS. We've had 4 delivery launches to date, and we have 8 active task orders for future deliveries and others in the queue and looking to be awarded. So again, just remember that we're in the early innings. So today we have 5 panelists representing 4 of which are direct CLPS providers, and another is in support of CLPS provider, all for missions that are to be executed in the future. But we will talk about some of the missions and deliveries that have already occurred. So let me just go down the line real quick and introduce everybody, and then we'll get started with the specific presentations. So to my left, we have Joseph Marlin, who's the Chief Engineer of the Blue Ghost Lunar Program at Firefly Aerospace. Next to him, we have Niharika Agrawal, who's a Project Manager at Intuitive Machines. Then we have Steve Clarke, who's the Vice President of Space Programs at Astrobotic. And we have Jeremy Fix, who's the Chief Engineer at ispace-US. And then Jacki Cortese, who's the Senior Director of Civil Space at Blue Origin. So we'll start with Joseph talking the Blue Ghost Mission 1 from Firefly Aerospace.
All right, thanks Adam, and thanks everyone for being here. I'm Joseph Marlin. I'm one of the 2 chief engineers on the Blue Ghost Lunar Program. Blue Ghost has had a busy year, and so has Firefly, and so we're going to go over kind of a retrospective of how our first mission went, and then a brief look ahead to what's next in store. Quick overview of Firefly first, fully integrated, vertically integrated company that also spans the launch, land, and orbit regimes of space exploration, with our Alpha small launch vehicle and our medium launch vehicle being developed in cooperation with Northrop Grumman to replace the Antares. Then we have the Blue Ghost lunar lander, which is what we're here to talk about, and then we also have our on-orbit line of vehicles, the Elytra vehicles. Some of the things that we like to talk about for Firefly that kind of point to some of the strengths that we have as a company is this vertically integrated model where some of the components that we fly on Blue Ghost also fly on our rocket, also fly on our Elytra space vehicles. We have a lot of in-house carbon composite structure expertise, from the very large structures like that MLV tank that you see in the picture to some of the smallest structures on the lander like struts. We do all of our own in-house avionics. We are an engine manufacturing company as well, and one of the challenges that we hit on this first mission was we lost the vendor who was building our RCS engines for us, and so we brought that project in-house and were able to fly those engines on our first mission, and we actually have one here at our tech demo table this afternoon. All right, so Blue Ghost Mission 1 landed on the moon in Mare Crisium on March 2nd of this year. This was a fully successful mission which operated all 10 NASA payloads and a handful of commercial payloads, almost 120 gigabytes of data downlinked from the surface, and that was utilizing what we are pretty sure was the fastest link ever established from the surface of the moon at 10 megabit. There were, as I mentioned, 10 CLPS payloads on board, and we've already heard from some of them here at this conference, like RAC and Lister and LPV, but some of the other ones include NGLR, which was a retroreflector, RADPC, which was a radiation-tolerant computing platform, LEXI, X-ray telescope, LMS, which deployed 4 probes out in the cardinal directions and then had a mast to map the lunar magnetic field. We heard from EDS, Scalps. It was on this mission, as it's been on a few, and will continue to be flying to continue to study the plume interactions. And then Lugray, which was able to establish the farthest GPS fix GPS solution so far to date. All right, we got to the moon using a 3.5 orbit trajectory. This made use of several phasing orbits in order to target our injection into lunar orbit at just the right time. This gave us up to 7 days of acceptable launch dates per month. It also gave us about 4 weeks of on-orbit checkouts and science operations. And so this was how, for example, Lugray was able to do their operations en route to the moon and kind of step up in difficulty, first getting a GPS fix from low Earth orbit, and then from a very far distance from Earth, then in lunar orbit, and then finally from the surface of the moon. While in Earth orbit, we also checked out a number of our onboard systems. We performed calibration burns, and we did health checks for all of the various payloads. After that, we performed our lunar orbit insertion, and this allowed us to spend about 2 weeks in lunar orbit where we continued checkouts. One of the things that we checked out in lunar orbit was our vision navigation system. This system is responsible for providing pose estimation, localization, and hazard avoidance and hazard detection on our way down to the surface. And so here you can see a comparison of some of the footage that we recorded compared to the onboard rendering of that, what we expect that location to look like. And this shows the strength of the shadow rendering engine and the overall digital terrain map that we had in. Unless you're kind of up there on the screen looking at the edge pixels, it's actually impossible to tell the difference. All right, as for the landing, landing was about an hour of completely hands-off nail biting for us operators. We did not have any human interaction with the landing process based on lessons learned from past missions. And so basically we begin our DOI burn with the main engine and all 8 Spectre thrusters. This sheds a lot of the orbital velocity. This is followed by a 45-minute coast period, followed by a braking burn, and then pitch over. And from that point on, the main engine is off, and we descend with only the 8 smaller Spectre thrusters. We perform 2 hazard navigation maneuvers, two hazard navigation detection checks, and then we can locate various rocks and craters that might not show up in the LRO footage. From there, we continue to descend until a soft touchdown. That's detected both from IMUs and from our landing gear sensors. All right. I know I have very limited time, but I can't not show this video. This is the footage of the actual landing. 4 different views. Top left is looking out onto the lunar surface, and this is looking down one of the sides of the spacecraft. Top right is the top deck image, and so there you can see on the left of the top right image is the flat panel. That's our high gain array and the Lugray antenna. And the rectangular prism on the right is the Lexi telescope. And then far right, there's a mechanism there. That's the LMS mast. On the bottom left is also looking down the side of the spacecraft. It's opposite the view on the top left. And you can see one of our thermal radiators has deployed. That's what the gold MLI flapping around is. That has revealed the radiator underneath. This is a totally passive system that we actually demoed at LSIC last year. This uses shape memory alloys to automatically open and close as needed. And so that system was exercised on orbit and on the surface. And then lastly, bottom right is another camera. This one is actually looking directly into the sun. And so the small circle you see on the top right is Earth, and the very large circle you see on the bottom right is the sun. All right, we've now completed pitch over, and we are continuing to descend to the surface. We have, during this process, while I've been talking, we've performed our hazard navigation, our hazard detection checks, and we're continuing to lower. At this point, the main engine is off, and we're using pulse width, carefully controlled pulses on the Spectres to maintain attitude and to maintain our descent rate. At this point, plumes become visible as those RCS, and you can see that pulsed impact from the thrusters are causing the kind of undulating effects of the plumes. this point now, we have cut off the engine. You can see a successful touchdown on the moon. All right, no rest for the weary, though. Within minutes of landing, it was back to business. While our mission might have felt like it was over, it was just beginning for all the payloads that this was what they were here for. And so we immediately deployed our X-band gimbal, and there it is going to face the Earth. This, like I said, had also mounted on it NGLR, which was used for ranging experiments from Earth stations, and then also Lugre, which was going to go ahead and get some GPS solutions from the moon using signals from satellites around Earth. We mentioned that SCALPS was on this mission, and so, oh, this is not a video. This is just a view of the various SCALPS images as we came down. We saw the Lunar Planet Vac deploy and operate yesterday, but it's a short video, so we'll watch it again. This was deployed using a fifth leg, or surface access arm, as we call it. And this was deployed to the surface with a gas spring and a HDRM. We also watched EDS yesterday, and one thing I don't think we saw yesterday was LMS. This shows some of those probes deploying. It happened really quick, but now you can see the tether spooling out. And here, reminiscent of the golf ball. 1/6 gravity is a very uncanny valley. And there's the mass deploying as well. And fully deployed with the Earth crescent. We saw Lister drilling as well yesterday. And we were really interested to see what those appear to be as kind of sparks, we think, from the gas that was used during that drilling. All right, so that was some of the highlights of the various payload operations on the mission. And so kind of an overview, all of these payloads met their objectives. And one thing we were able to image was the eclipse. There was a total solar eclipse as viewed from Moon, and this was not planned as the baseline mission, but due to our landing date, we were able to view that. One thing that we were contracted with NASA to do is view sunset, and so we were asked to operate 5 hours into lunar night and operate a number of the payloads. This allowed for both some unique opportunities for payloads to kind of get a control reading of what their data would look like without the sun. And it also allowed us to visualize this levitation phenomenon that some of the Apollo astronauts were able to report. And so we saw that as that glow on the horizon, which is not easily explained with the lack of atmosphere in any other way. All right, a bunch of anomalies. We calibrated, we counted about 60 different anomalies and dispositioned them. Most of them were not mission threatening. I'm probably out of time to talk about all of them, but we do have a table and we can talk about them. Some of the most interesting ones, we did have a lot more ground effect during landing than we expected, and so instead of throttling down to hit the ground, we actually ended up hovering a little bit until we continued to throttle down. And then we also landed next to a giant crater, which acted as a parabolic cooker on the lander and absolutely devastated our initial predictions of a thermal environment, and required some very innovative scrambling on our parts to keep the lander safe. This included using the X-band gimbal as a sunshade and some quick requalification of various components at higher temperatures. All right, I'd like to say that this was just an easy lift, but in fact, this was an extremely difficult thing. One of the benefits, one of the reasons we think was just because of the amount that we empowered each subsystem to take control over their own destiny and own their systems. Also, we'd like to talk about, we like to say that a lot of the success was due to the amount of testing. We had over 500 hours of sims, 8,000 operator hours of sims, so an incredible amount of preparation went into this. Anyway, looking forward, what's next? We got mission 2. Mission 2 is going to the far side, and so with each mission, we're trying to bite off another capacity. This mission will include a relay, which will provide the ability to store and forward and do bent pipe communications to this to our lander on the far side of the moon, which will be doing a bunch of radio astronomy studies using the moon to kind of shield a lot of the radio noise from the Earth. That's fully manifested, but what's not is mission 3. This was just awarded, and this will also include a transfer stage as well as a lander. And this ultra dark will also remain in orbit as a comms relay. This is going to Groot Highs and Domes and will include a rover. So as mentioned, each mission adding new capacities. This will have a mission, rover mission operations, as well as continuing to build up that comms relay network at the moon. Okay, that's it, and I will pass it over to Intuitive now.
All right, thank you. So, hello. All right, so hello again. Yesterday you heard me talk about Hopper, and today I'm going to talk about our landers. We're going to focus on IM-2 and IM-3, but I'm going to touch on our first mission last year as well, which was our IM-1 Odysseus mission. You may recognize it. We landed in the South Pole last March, and it was the lander that landed furthest south on the lunar surface, a record broken only by our second lander this year. So that's our IM-2 Athena mission, which is where Hopper, the Trident drill, as well as the Nokia experiment flew on. A couple pictures here from encapsulation. We have both IM-1 and IM-2. We have 2 more missions coming up. We have IM-3 and IM-4 coming up in the next 2 years. So hopefully more pictures to follow. The picture on your right is a picture that you've probably seen many times in the last couple days. So that is the 2 pictures here are the beginning and end of mission of our IM-2 mission. On the left, you have soon after LVSEP, and on the right, you have our surface operations. We launched on February 26th this year, landed on March 6th. Our transit's only about 10 days, 9 to 10 days, where we spend about 3 to 4 days in open coast to the moon, and then 3 to 4 days around the moon in orbit. So it's a much quicker transit. We're doing burns every day, which also account for a much more stressful mission operations. And we're going to talk about kind of the lessons learned from all of that in a bit. But I did want to mention I had the honor to do mission ops for both our missions, IM-1 and IM-2. And as I mentioned to someone yesterday, the color purple has never looked more terrifying until it's the color that you're staring at while you're waiting for telemetry from your lander. So this is a video of our lunar orbit. Little shout out to Hopper over there. That is roughly, I believe, 80 kilometers off the surface. Like I mentioned, we were in lunar orbit for about 3 to 4 days, and a large part of that is confirming that we're ready for landing. So we're doing health checks on our sensors ongoing throughout transit. During orbit, we also do payload checkouts with a lot of our customers, making sure that their payloads are ready for as soon as we get to surface operations. And then these 2 are actually videos of our landing sequence. So this happened on March 6th, and you'll see it from 2 different perspectives. So IM-2 Odysseus gave us some of the closest imagery we have of the South Pole, and you can see how much of the surface is actually in shadow and how dangerous and hazardous that terrain is with the number of craters and boulders in the way. As Joseph mentioned earlier, like HDA, hazard detection and avoidance, is a major part of all landers. We also run those same type of algorithms that are using our optical nav system to determine not only our pace or our velocity and direction of travel, but also where is that safe spot. You predefine a safe spot in your mission ops going to start with, but the terrain, you don't get as close, we don't have imagery that's to the resolution we need to fully determine that that is going to be a perfect site for us. So HDA is a big component of what we call LDO, so our lunar descent orbit. That's when we're closer to the moon, about 20 kilometers up. and that gives us a lot more detail and imagery. We stay in that closer orbit for a few hours, and that's where we did our laser checkouts. And I'm sure there's some questions about that, and I will get to that. But I did want to touch on all the partners that make it possible. So these are our partners at Intuitive Machine across all our projects, not just our landers, but we have a bunch of NASA project partners through CLPS, through STMD. We had a large number of payloads through them. We have a lot of international partners and corporations that work with us too. Mentioned the German Space Agency before. We worked with Nokia, we worked with Lunar Outpost, Lone Star. So we're always looking for new corporate and international partners. And then we also do a large amount of work with universities. A lot of our navigation and testing partners are universities, so they're kind of listed there. So Embry-Riddle was actually a payload on our IM-1 lander, Eagle Cam, that was going to deploy and take an image of us while we land, a third-person selfie, if you will. So we're also always open to student payloads and flying them as well. So the thing I really wanted to focus on were the lessons learned. We've flown 2 landers now, and in our first mission, IM-1, we discovered about 85 issues that we had determined we needed to solve going forward. We had solved all 85 for mission 2. We did not see a repeat of any issue to the same flavor that we saw them on IM-1. So that was a big aspect of our retrospective, what we call our hot wash after mission. So where we every sub-team has an opportunity to talk about both the project build and design phases, but also the mission itself. And it was a week-long hot wash for IM-1, and we gave every opportunity to talk in a very candid manner of what went right, what went wrong, and what can we fix. So that lent itself to continuous improvement and making sure that we weren't going to have the same issues. Part of that was looking at how we test. As mentioned before, testing is a big component of making sure you're successful. And we have a large number of different interfaces and venues we do testing at. We mentioned some of the Hopper ones yesterday. We have our own flame range that we do our engine firing. So if you ever want to see what a Nova C engine looks like, look up a video online and you should see some beautiful firings there. But our flight engine is tested on the ground before it goes into flight. We have a lot of EDU testing that we do constantly to make sure we're improving our hardware. And we have a flat sat bench where we test every unit, every EDU unit and flight unit on the bench before it gets onto the flight hardware, the flight vehicle. And that allows us to test as we fly. So we're testing in environments that look like our flight environment to the closest degree possible. So that includes testing through TVAC, through Vibe. And that ensures that you're able to mimic an environment well. There are gaps, and that was, as we kind of discussed, laser is the big gap that we had. We found an issue on IM-1, and we solved that issue for IM-2. We tested the lasers on the ground through a series of navigation testing. However, we didn't catch a different issue, which came, and we're still investigating, coming up with the final report there, but it looks like it has some to do with interaction with the lunar surface in a way we weren't expecting. And that's where you kind of have to deal with contingencies. You can't actually test perfectly as you fly. You're not flying 20, 80 kilometers above the lunar surface on Earth. That's just not possible. And so you need to have some sort of contingency management that allows you to be able to handle such issues as they come up during mission. The big thing we learned, especially for IM-2, is that there's multiple types of contingency management. There's management that comes from issues where you have a longer period of time to solve. So it's something you could have found maybe in COAST, a thermal issue that you're seeing could trend negative, but isn't yet, and you have a significant amount of time to solve them. The way you respond to that sort of issue is different than what would have happened with our laser, for instance, where we are hours away from landing, and we need a quicker response. And you need to build those contingencies up in your training early on. So mission ops in general for these sort of missions is complex. it's a complex engineering task. It's not just a mission design task. It's keeping your engineers in the loop and making sure that you're aware of not only the mission priorities, but of your fault tolerance, your risk analysis as well. So that's something that you're continually improving on and adding contingencies. That's going to be a major part of our upcoming IM3 and IM4 missions. We're always looking for new partners, so come find me if you ever want to talk about the previous missions or the next ones.
Thank you, Niharika.
Well, yep, good afternoon now. Thank you for having us here today to talk about getting gear on the surface. And I want to congratulate my competimates here, both Firefly and IM. Firefly for a fully successful mission, and I am reaching the surface twice now. I think we all know that it's very difficult. A lot of lessons learned, as we've talked about. And actually, I was surprised to see 60 anomalies you guys were tracking because you made it look easy. So congratulations. And we're looking forward to being able to deliver ours by the end of this year. So with that, I'll just, in the interest of time, move along. Lunar delivery, that's one of our key capabilities at Astrobotic, obviously. I wanted to just show our Peregrine lander sitting on top of the payload adapter, getting ready to be encapsulated in the first Vulcan launch. And this was roughly 18 months ago. I think everybody knows that we did not reach the lunar surface. We had a problem with one of our propellant valves early in the mission that overpressurized one of our oxidizer tank. And it was an interesting time. I was not there yet at Astrobotic, but I certainly have worked with the team that was there. They were able to recover basically a crippled spacecraft and fly it for 10 days in cislunar space. We were able to activate all of the payloads. Two principal investigators, as far as I know, have published peer-reviewed papers on the data they did receive. Although we didn't reach the lunar surface, we were actually able to elevate most of our subsystems to TRL 8 or 9, and that feeds into our next mission, which is Griffin Mission 1. This will be the largest lander, commercial lander, to go to the moon through the CLPS program. Kind of call it a medium-class lander, capable of delivering 650 kilograms to the lunar surface. That is a picture there in our clean room. We were doing a fit check of our solar panels. That was about a month and a half ago, and work continues. I'll talk about some of the progress here. Mainly our main payload is Astrolab's Flip rover. Great team to work with between Astrolab and Astrobotic, and so we're really looking forward to delivering that rover to the lunar surface. And we also have a couple of international payloads as well that I'll just briefly touch on here. So here's a video. Not sure if you need to activate it or...
Just hit next again.
Yeah, there we go. So I decided not to play the music. I won't walk it through, but this is a rendering of Griffin delivering the Flip rover to the lunar surface after a ride on a SpaceX Falcon Heavy. As I mentioned, our launch window opens up in December, and we hope to show a year from now at the LSIC Spring 2026 meeting actual video like Firefly did with their mission. As you can see, we've landed in the South Pole region, and the Flip rover will be deployed onto the surface via ramps and a tether. Once they've activated their rover and they're ready to go, then the tether will be detached and Flip will go off and achieve their mission objectives. And as I said, we've got some additional payloads that will be flying on board, so the lander will continue to operate for 14 days and acquire data for the principal investigators of those payloads as well. So one of those is being developed by ESA. It's called LandCam X. It's essentially a camera that is testing out some navigation algorithms with the intent to improve the accuracy of landing for future landers. So we're excited about taking on this international payload. And also, I'll talk a little bit more about Cube River Run here in a couple slides. That rover has been developed by Astrobotic. It's an in-house development, but we are partnered with as a joint mission with Mission Control Space. It's a Canadian company that's being funded by the Canadian Space Agency. They've developed a software platform called Spacefarer. Once we've deployed Cube Rover onto the surface, we will, as a company, will basically drive our rover on the lunar surface, check out some systems, and then we'll turn it over to Mission Control for them to do some mission objectives with their software package. So we're pretty excited about this joint mission, and again, it's another international partnership. So there's another picture, more close-up of the Griffin lander. You can see it on the stand in our clean room. Again, those solar panels are now off and being finalized while we're doing some additional AI&T work on the spacecraft structure itself. So some key components here, propellant tanks. On the far left is the qualification tank for the tanks that are being made by Vivace. And then the picture right to the lower right of it is flight tank number 2 being welded together with the barrel section and the dome sections. They've made much more progress since then. These pictures are probably a month old. And then on the right, the qualification axial engine being built by Frontier. It just finished up shock vibe last Friday. And we are looking at the data along with Frontier on that. We're looking forward to actually doing the qual engine hot fire here, hopefully in June. Frontier will be running that at their test stand. That's actually at Squadron in Victorville, California. So we're getting very close to getting flight engines as well. And then on the far right is, it's kind of a faraway picture, but that's our Universal Test Campaign test article. This is a mobile test article that we originally built when the Viper rover was going to fly. NASA wanted us to do some additional testing to increase the confidence on the propellant and propulsion systems. We decided to keep that with in partnership with NASA to go ahead and do that, even though Viper is no longer flying on Griffin Mission 1. That test article is near completion. It'll be done in about 2 weeks. And then we'll be sending that out to Squadron as well. We'll be doing cold flow testing and hot fire testing with some ground thrusters to characterize the propellant system, which mimics the Griffin lander propulsion system. So it'll be always good to see some smoke and fire coming out. TRN and hazard detection. We have developed our own TRN HD system. And in fact, just within the last couple of weeks, we successfully completed sims with injecting issues to adapt to those issues and do successful landings on the lunar surface from a flight sim standpoint. So very proud of the team of working through those sims. We'll continue to do those, but we're pretty excited that we made it through the simulations to date. Now I'm going to show you a video in the next slide, but you'll see on the right is our Zodiac vertical test, vertical landing suborbital rocket that we fly out of Mojave, California. The reason I'm showing this is we flew our TRN HD system on board that over a simulated lunarscape that we have out there called the Lunar Surface Proving Ground. You can see in the top right and then on the bottom right at a nighttime shot of that. It simulates a lunar surface. Not only have we developed tested out our TRN HD system, but other commercial companies and have tested out some of their landing algorithms as well using our Zodiac vehicle. So this is just a quick video to show an actual flight. It goes up to 500 meters, and you can see the Lunar Surface Proving Ground over there to the left on that, and then it returns to the same launch pad. And this vehicle has flown over 600 times. In fact, they flew a free flight yesterday. So full manifest on that. It's a good test bed. Cube Rover Mission 1, I mentioned earlier. Here's some pictures here of the engineering model on the top left. We sent that to Mission Control in Ottawa, and we actually were able to send commands from Pittsburgh, where our Mission Control Center is, to the rover in Canada in their lunar surface test bed. And then when the engineering model came back, we reversed that, and Mission Control sent commands from Ottawa to our headquarters in our test bed, all successful, and so we'll continue to work some of those tests. And with that, just to let you know that the flight model is near completion, and we hope to have an announcement here in a few weeks on the progress of the flight model itself. We've tested out the deployment system for the lander itself, all successful there, so we have a lot of good progress going on, and we're looking forward to sending Griffin and the flip rover and those payloads I mentioned at the end of this year. So thank you.
Hi, everyone. My name is Jeremy Fix. I'm the Chief Engineer for ispace-US. And before I tear into it, I want to thank LSIC for putting this on. This is fantastic. APL for hosting. Adam for corralling us all up here and making us behave. And our fellow panelists. But most of all, I want to thank you, the audience. If it wasn't for your passion and your interest, there'd be no point in us being here today. So thank you for attending. I know I'm going home this week re-energized, ready to get back after it at work. While I represent ispace-US, a lot of the successes and accomplishments I'm going to be talking about here today are really owned by my Japanese and European colleagues in Luxembourg. Just want to acknowledge that. It's a lot of their hard work, their accomplishments that we're building on. Part of our vision is really trying to work backwards from a lunar economy in the future. I think you can get caught in the here and now. What am I doing today? But you really need to be looking forward, where are we going to be in 15 years? Where are we going to be in 20 years? And I would encourage you, I don't have time to talk through it today, but I would really encourage you to go Google Moon Valley 2040. Look at our long-range plan as a corporation. I do that myself. Some of the days you get frustrated, you get kind of stuck in the mud. Jump on there, look at the future, look at a lunar economy. You can't have an economy without people. I guess you could build a robot economy, but there's a lot of sci-fi says that's not a good idea. But really building forward and really thanking everyone here for the openness. We're treading new ground together. We're going places no one's gone before. Really, ispace-US, our parent company, iSpace Incorporated, founded in Tokyo, Japan in 2010. We have since grown strategically across the world in Luxembourg and Europe and here in Denver, Colorado. That's intentional. It's a global footprint, global collaboration, not only with the international agencies, JAXA, ESA, NASA, but we also have access to the global commercial companies. One key and right now we're a little over 300 employees worldwide, 100 in the US, and I'm very proud to say we have over 30 nationalities represented within the company, so we truly are a global company. One key enabler, we were able to secure a State Department approved technical assistance agreement with Japan and Luxembourg, which means we can freely share lessons learned, successes, technology, not only in software, hardware, across the board. That really kind of helps us work as an international body. Within the ispace-US, to date, we've had over $120 million of investment in our site in Centennial, Colorado. A lot of our vertical integration is occurring there, a lot of our propulsion system building, avionics. This also houses our Mission Control Center for future missions coming up, in addition to the one in Tokyo, Japan. Our team right now in the US is sitting on console with our Japanese colleagues with Mission 2. As that mission completes, that same team will come back to the US and sit on console for Mission 3. So we have a continually trained up group of mission operations globally that can support each other, and both of these sites can act as a backup to each other for future missions. Kind of walking through hardware on the left, Luxembourg is really our mobility expertise. Right now we've got the tenacious micro rover. about 1 kilogram of payloads. It's great for local area sensing, interrogation of the regolith, manipulation. The Resilience Lander, that is the first mission out of Japan, delivers about 30 kilograms to the surface. It's right-sized for a ride share on a Falcon 9, and in fact, Mission 2 was co-manifested with Firefly Blue Ghost, January 15th. They got there a little bit sooner, but it's not a race. And part of the realization is that you're making a huge investment in going to the moon, not only in the launch vehicle, the people, the capital involved. You really have got to up the amount of mass you're taking to the surface. And moving forward into the future, Apex 1.0 is the vehicle being designed here in the US, complementary with the Series 3 lander in Japan. Both of these vehicles share a lot of common components, including the engines, some of the avionics to the extent possible. The differentiator there is that Apex 1.0 is dedicated or really designed around the Falcon 9 GTO capabilities, where the Series 3 can also support the Mitsubishi H3. If you have a customer with domestic sourcing requirements or certain launch requirements, we can support either. Talk a little bit through Apex 1.0, our US lander. It's a large vehicle, not as large as some others up here, but we do have the ability, multiple payload zones, standard interfaces. We offer a lot of compute capacity on the vehicle. Your terrain relative navigation, hazard avoidance requires a lot of computing capacity. We make that available to our payloads after landing. We did stick with storable propellants, a lot of propellant margin coming in and landing, really trying to bring in exquisite landing capabilities for our customers wherever they want to go. Bigger picture, I think the lunar scape is evolving to where you have these very large landers that'll have maybe a very large anchor customer that'll take a lot of people to one site. Kind of the SpaceX transporter model. I kind of compare that to the cruise ship model on Earth. If you want to go somewhere fun, you can leverage the capacity of buying power of a bunch of people, but unfortunately you don't control where you're going. You're going to sit in the same stateroom. You're going to have the same meal plan as everyone else. Where we're targeting is customers who want to go have a specific location, a specific time, a specific mission that they want to go to, where we can provide really a full end-to-end mission as a service for outliers that really have special requirements or special capabilities required. We also are developing, as part of our commercial mission 3, for anything going far side, you don't have direct-to-earth communications capacity. We're developing multiple instantiations of the same vehicle of a relay satellite. Provides high bandwidth direct-to-earth communications relay services that will service the lander on the surface during its primary mission. These will carry on and continue to operate long after that mission terminates. There is relay capacity. We're looking to use that some of our own landers, but that's also available for other customers if you need that service. I would point to, back to my previous slide, looking at these landers, there's nothing that would prohibit these vehicles from living for years and years on the lunar surface if you can survive that brutal lunar night. And we do have a couple of strategic cooperations in place with Volta Space Technologies and Xeno Power to really start trying to build these vehicles to where they can not only survive the lunar night, but operate through. Hop through that. Really kind of the most exciting is Mission 2. Again, it launched with Blue Ghost on January 15th. It is now in lunar orbit around the moon. We're coming up on a landing here very soon. The vehicle itself, some commercial payloads, as well as the micro rover out of Luxembourg. Some pictures. I think if you go on the internet, there's almost as many pictures of the moon as there are of cats. But this one is special. This is really our success number 5 of our lunar flyby and our low energy transfer. Another shot looking back to Earth. If you're sentimental like me, this is a little bit of a sad photo. You've got an explorer leaving home, never coming back, kind of looking back over your shoulder, knowing you'll never return. Mission 2 milestones. There are currently 10 of them. We're right now at success number 7. We have entered lunar orbit, and are rapidly approaching the most, probably the most critical and most complicated sequence of events to actually get to landing and touchdown. I would invite everyone to join us in the landing party, June 5th, 1524 Eastern Time. You can scan the QR code. I promise not to rickroll you. Or you can go to the iSpace landing site. There's a lot of information, not only on the mission, everything leading up to it, but it's going to be very exciting. We'd be honored if you would join us. Post-landing, where the mission really begins, is the mobility portion of the mission, where we will deploy the rover. Again, we're not calling these milestones or gateways. We're calling them ventures because you have a mobile asset. One is getting it, commissioned, deployed, operational, moving around. I'm happy to note this will be the first European-designed rover that is teleoperated on the moon. It does have a scoop, and another kind of a novel feature of this is we are going to actually collect lunar regolith, and under the Artemis Accords, do a transfer of ownership of that regolith from ispace to NASA. Even though it's never going to come home, we're starting to exercise these stepping stones to getting us to an economy on the moon. Last one I'll close out with, our own mission out of the US, it's the Team Draper Commercial Mission 1. This is the NASA CLPS CP-12 mission. We're proudly supporting that entire payload manifest, as well as a few more commercial payloads on board. Would be very excited to be able to come back here about this, late 2027 and tell you all about this mission when it closes out. So anyway, thank you everyone. I appreciate your time today.
Thank you. Hello. Can everyone hear me okay? All right, awesome, thank you. Hi, I'm Jacki Cortese. I'm Senior Director of Civil Space at Blue Origin. Just wanted to start by saying that I've been at Blue Origin for 8.5 years. And the entire 8.5 years, I've been lucky enough to be working on enabling our lunar projects the entire time. So I'm very excited that we're making our first moonshot this year. It's been a long time personally for me, so I'm very excited. And I would just say a longtime LSIC fan. So thank you all so much for having me today. For those of you here yesterday, some of these charts will look like John's. He stole them from me, not the other way around. But I will hopefully tell you some things that you didn't hear yesterday from him. So for starters, one cool thing is that Blue Origin is making 4 moon attempts this decade. So prior to 2030, which I think is something that a lot of people might not know. So our first one is the Mark 1 lander, the lander in the center of the screen, which we are attempting a South Pole landing this year, 2025. And if successful, it'll not only be the largest lander to ever land on the moon, but also the only LOX hydrogen lander. So that's a commitment by Blue Origin, a long-term commitment. We consider ourselves a bit of LOX hydrogen experts. We've been doing it for a very long time on our New Shepard vehicle that hopefully people have seen launch and land on a regular basis. And so that's a big one for us this year, is that first Blue Moon Mark 1 lander. Our second Blue Moon Mark 1 lander is also in assembly at the exact same time as the first lander going to the moon this year. So that's very exciting. We have a dedicated facility in Port Canaveral, Florida, where we're building all of our Mark 1 landers. We intend for it to be a production line capability. It's a 3,000 kilogram class lander. We went straight for an infrastructure class single launch capability, so I'll talk about that more in a second. Our third mission to the moon is going to be our uncrewed human landing system demonstration. So that team is hard at work also down in Florida building our systems for the human landing system program. That uncrewed demo can also fly payloads as well as both of the Mark 1 landers. So that's our third mission planned to the moon this year. And then prior to the end of this decade, we'll be landing 2 crew on the lunar surface for NASA in partnership with the Artemis program. So So a lot on the plate for the team, but we're very excited about these opportunities and these various moonshots. So it's very exciting for us. But mostly here to talk about Mark 1 today. So we'll quickly hit on some key points that hopefully are something, again, that you didn't hear yesterday. But again, this is a 3,000 kilogram class lander, and it flies on a single New Glenn. Hopefully people tuned in January. We flew New Glenn for the first time and achieved orbit within pinpoint accuracy on our very first mission. So that was a huge moment for Blue Origin and a key enabler of everything we're doing in our lunar permanence business unit. So this lander is powered by one BE-7 LOX hydrogen engine, 10,000-pound thrust engine, which again is part of a broader Blue Origin commitment to using LOX hydrogen as our core propellant mix to unlock the greater solar system through technologies like zero boil-off, other cryocooler technologies. This first mission this calendar year I'm so excited. I actually have so many hardware photos, but we're saving them for Twitter, unfortunately, so I did not show them. But Mark 1 is very far along in development, as you would in assembly, as you would expect for a lander flying to the moon this year. You'll just have to take my word for it right now, as this is a render. But we're actually in final assembly right now to ship the vehicle out to NASA Johnson Space Center here very imminently for testing at Chamber A, which is we're very grateful for that partnership with NASA. After that, we will head back to Cape Canaveral with our cute little Mark 1, and we will launch it to the South Pole of the moon. The transit's about 7 days from launch to landing, and again, headed to the South Pole. One thing that I think is really cool, and I know we're all probably huge procurement nerds here, so we are a CLPS vendor, which a lot of people don't know. We are on the CLPS catalog with the Mark 1 lunar lander, and one amazing partnership, and we're so grateful, is that CLPS realized, in partnership with Blue Origin, we're not going to miss a shot at the moon here. We're not going to miss an opportunity to fly some really exciting science to the moon, despite the fact that Blue Origin fully self-funded Mark 1, and there was no government resources that went into this vehicle. So CLPS did a partnership directly with Blue Origin, and we are flying a plume surface interaction camera system in partnership with CLPS, SCALPS, which has been mentioned by several others, and I think the message and what I think is so cool about this that I'll share is we should not, as a community, be missing any of these missions to the moon. We should maximize as much as possible. Everyone here has lots of missions going, and certainly we should make sure we're getting as much data as humanly possible. So again, very grateful to Adam and his team for going a little bit outside of the typical task order process to make sure we're getting valuable data in plume surface interaction from an engine that is significant, 10,000-pound thrust engine. So that data is going to be very valuable for this community and for all of us as it comes to that important regolith interaction. So again, very grateful for that, and to be a CLPS vendor and to be a CLPS task order provider. And like I mentioned, our second Mark 1 is simultaneously in assembly. So our facility in Port Canaveral has one lander almost done and a second lander in assembly. It was really important for us to procure all hardware for 2 Mark 1 missions years ago. I think that's a key finding, is that supply chain for single-use items is very, very difficult in the space business. So we went ahead and procured all hardware for 2 Mark 1s several years ago. So that lander is in assembly, and ideally we'll have a successful first mission of Mark 1, incorporate any findings and be ready to fly again. But also in the event that, there's more to do, or, the mission doesn't achieve all of our objectives, we have another lander ready to go. That was something that was really important for us, and we do have payload space available on the second Mark 1 for those people that are looking to go to the moon here soon. So that's another exciting thing. John showed this yesterday, again, stolen from me. I actually made this chart, but just to show you all some hardware, since I wasn't allowed to show the lander. But we have Mark 1 hardware for the BE-7 engine on 4 simultaneous test stands. So hardware rich is a key part of what we're incorporating into our lunar efforts. So these are just some examples. We're starting the engine nearly daily at AFRL in Vacuum in California. We have 2 stands in amazing partnership with NASA Marshall in Huntsville, and we have our own private engine test facilities in West Texas. And before I conclude here and let you guys get to questions, I did want to say that we are very, very thankful for all the work that we do with NASA, and I just wanted to share some opportunities to work with Blue Origin. For example, we've been working with STMD pretty much since the beginning of Blue Origin, largely through the Flight Opportunities Program. For those of you that are unfamiliar, it funds flights on vehicles like Blue Origin's New Shepard. And that vehicle has been a test bed for us to advance all of our lunar capabilities, like John mentioned. We've flown DDL sensors on the booster, and we recently, in partnership with STMD, actually flew a dedicated lunar gravity mission. We've spun the New Shepard capsule to simulate several minutes of actual lunar gravity here on Earth. It was a fully booked mission by researchers, NASA, and Blue Origin to test our capabilities long before we ever fly to the moon. So that is an amazing mechanism, and I would highly encourage everyone to look into it. Many tipping points that we're so grateful for with STMD, our deep partnership with CLPS, who I will just say, being the lunar lander experts at NASA, they help us with so much more than just our little task order. So we're very grateful for that. And then, of course, the Human Landing System program. We would love to talk to you guys about payloads, so find me whenever. And yeah, please keep your fingers, toes, anything crossed for a successful first Mark 1 mission this year. Been a long time coming for a lot of people at Blue Origin, so we're very excited. So thank you.
Yes, I want to thank all the panelists again for talking about some of which is behind us today, but more excitingly about what's in front of us. So definitely an exciting time for CLPS and the broader community. We do have a little bit more than 10 minutes for questions, and there's several in the queue. But just a reminder that please enter them if you have one. And we'll jump right in with the kind of the highest voted one, and I'll start it with Joseph. CLPS is definitely a community, but it's also a competitive environment. How do you balance preserving your competitive advantage and collaboration and data sharing between other lander providers?
The other chief engineer on the Blue Ghost program, Dr. Coogan, was talking to an old colleague of his just the other day who worked on the Apollo missions at Draper. They met in university. And his colleague was saying how it was a shame that a lot of the data they have from his work, he was in GNC for Apollo, and a lot of his work is gone. And so that kind of inspired us to continue to do what we've already been doing, which is applying to a lot of conferences and submitting a lot of abstracts and papers. I already know for a fact that we'll have papers coming out from the flight dynamics team, our propulsion team, our thermal team, and a lot of the other teams will be continuing to publish those papers so that all of the learnings that we have can be applied to other companies and for the United States and humanity in general to continue to take steps forward in the exploration of space together.
I'm going to echo a lot of that. Many of you are probably really familiar with some of our execs, Tim Crane, Steve Altimus, Ben Bussey. They come to conferences regularly and like to talk about our missions. Also, a large part of why I had a specific lessons learned slide today is I wanted you guys to get the information you're not seeing online. You can learn about the lander capacities online, but the detailed workings of how we did mission control and the lessons learned from an operator and those of us in the room are important. So conferences like this, to LSIC and APL's credit, is super important to bring this community together and having these open discussions and being candid with one another about what works and what doesn't work. This is super important.
Yeah, and I think I mentioned during my talk, I said competimates, and that's really the culture I think that NASA CLPS has built with the CLPS task orders. We are competitors, but we all want each other to succeed because we really need everybody to succeed if we're going to develop this lunar economy that we all want to get thriving, right? We're right at the nascent steps of it now with getting to the lunar surface, and we just need to continue to have successes to build that lunar economy, not just for the U.S., but really for a global community. I mentioned too that Peregrine had an issue, and we released a review board report last year, about a year ago now, so that we could share those findings with the broader community so people could learn from what we experienced, and so they did not have to go through that as well. And I think that had a ripple effect too, all the way down to the supply chain. Jackie mentioned supply chain. It is so critical, I think, to have a strong supply chain for all of the CLPS providers going forward, and that means multiple missions that need to be awarded. I know Adam and his group are looking at a CLPS 2.0 eventually, and we hope to see maybe a more robust supply chain structure there where multiple missions are awarded so that we can really secure a good, strong supply chain base, again, for this lunar economy that we all want to establish.
I view this as we're not trying to corner the market, we're trying to build the market. Everyone here is helping each other to do that. We don't know where it's going to head. We don't know how big it can be. But knowing that we're collaborating, we're working together to build the market, to build room not only for everyone here, but for others that want to enter it, to build it on. And I really look at it as we're the incubators, not the competitors. It's a huge market, a huge potential, and it would be very short-sighted to try to grab onto a piece of that and not grow it together.
Yeah, I totally agree with what everyone has said, and we're very grateful for how open all of the preceding missions have been. We've incorporated a lot of findings from the preceding lunar missions into our conversations. We've challenged ourselves, and we're so grateful for that openness that everyone has shared. So I'd say that first off. And second of all, we're always looking for opportunities to collaborate, and like Jeremy was just saying, the CLPS community is the perfect place. So for example, with some of our visions for in situ resource utilization on the lunar surface, a key enabler of that is mobility. And so we've always had mobility visions at Blue Origin. And a couple years ago, we acquired Honeybee Robotics, who are experts in off-world mechanisms and mobility type work. And we, because of this, wound up partnering with Firefly for their mission to the Groot-Hyson domes, and we're the mobility provider for them for that mission, which is very exciting. So it's just another example of how, I agree with you totally, CLPS is an incubator for broader collaborations. It's not just one of us, but all of us, and we're always looking for opportunities like that. So we're grateful to be partnering with Firefly on that.
Thank you. All right, next one I'll direct to Niharika, and then I'll see if Jackie or others have any comments. And several folks talked about the challenges with the South Pole landing sites. What are you considering for de-risking some of those challenges for future missions?
So we've talked a lot in the last couple days about testing, and I'm gonna go on a little bit more about that. It's characterizing your testing to fit your environment. So some of the challenges we've talked about at South Pole are long shadows or really deep craters and a lack of imagery that we have currently. So you start building newer navigation algorithms that help you use different sensors. So we wouldn't necessarily use the same sensors we used in a previous mission for maybe a further South Pole mission. We look back at our lessons learned and how we interacted with our sensors, what the performance for our IMUs were like. How clearly did we see our imagery from our cameras? And we got a lot of imagery during this last mission. So we're really looking at all of that in intense detail to determine, do we need new sensors, or do we just need to advance our algorithms? Do we need to test in a sandbox that allows us to mimic regolith reflection, for instance, or study our cameras in an area where we could create these long shadows created by craters and check what our performance is looking like there.
Anything you want to add?
Yeah, I'll go ahead and add. I think, South Pole presents a lot of unique challenges. Our landing site was in Mare Crisium, which is kind of mid-latitudes, a little north, but mostly, mid-latitudes. But we did land very, very early in the lunar morning. We've looked at our vision navigation system. It's, we think, resilient to sun angle of down to 2 degrees. So we think it would be pretty robust, and it certainly was very robust on our first mission. But that said, I think we're going to continue to watch progress of other landing attempts and continue to keep our eye on other sensors, perhaps leaving the visual domain if we need to.
Next one I'll originally direct to Steve, and then I'll poke Jeremy and see if anybody else has a thing. It's beyond a successful landing, what are the most critical operational data points or feedback mechanisms your teams need from the lunar surface to inform future mission design and improve reliability for subsequent deliveries?
Well, that's a good question. I think to touch on what we were just saying right here is landing in the South Pole environment is hard. Right? We can land at the mid-latitudes and so forth, full sunlight, but I think the fact that we're going to be landing on the South Pole as well, and that's where we think, again, we're going to have a human return presence there. The more we can land there, the more data we can get from all of these landings, and then share this data will only improve the accuracy and the precision for our landers and the future landers, even the human landers as well. Which is critical. So if we're going to build a base basically in the South Pole area, we need to be able to land with really good precision in different areas around the South Pole so that we can expertly build out the infrastructure that's needed there for more permanent presence. So again, coming back to these early shots going to the South Pole, the more data we can get from these landings and we can share across so that we all can really refine and dial in our precision landing, hazard detection, and so forth, I think is critical. And then we can start laying in the infrastructure that we need to put in place, such as power, so forth like that.
Anything you want to add?
Yeah, from our perspective, all data is good data. Some of it is useful. We've been extremely lucky to have access to it, to other pathfinders already. A lot of lunar maps in Viz have been done. But again, South Pole gets tricky because the scene doesn't look the same as it does in the picture, right? You've got shadows, you've got the sun playing tricks on you, you've got the sun trying to blind you perhaps. And a lot of that is moving to sensor diversity, moving to sensors that don't rely on sunlight. And again, moving forward into the future, we're going to want to be landing on unlit surfaces. There might be items that drive that, better terrain sensing. And really, the best way to drive that is modeling what you can, test, and there's really no replacement for that. Test what you can. In relevant environments. It's easy to fool yourself that you have a solution that works. It's a little bit harder to really bang at that until you know you have a bulletproof solution.
Have time for just one more question, and I'll start down with Jacki and work our way back. One of the big tenets of CLPS is lessons learned and lessons applied, and we saw that kind of mentioned in multiple of the presentations. So I just want to ask everybody kind of to identify your one or two kind of key lessons learned to date, whether it be in the lead up to a mission or in the execution of a mission, and how those are being applied to future missions.
Yeah, that's a great question. Like I mentioned, we are very grateful for the lessons learned shared by others, and we have incorporated that, as I've mentioned. I would just say for us, the biggest lesson learned so far has just been hardware richness in some of the supply chain issues that I think we've all encountered. It can really make or break your mission. So like I mentioned with our BE7 example, I think we might have been a little slow going at the beginning because of, issues with hardware richness. And so the number one thing we realized that we could do is, partner more, acquire as many stands as possible, and frankly, even if it doesn't work, test as much hardware as you possibly can. And so, like I was mentioning about never missing an opportunity to take something to the moon and learn something, we've tried to never miss an opportunity at a test stand, never miss an opportunity on New Shepard to fly and advance something, because hardware richness and making sure that, you've done as much as you possibly can before taking that moonshot is something that we're trying to apply. So that BE7 example is probably the best one from us.
From my perspective, I'm a technical animal. I want everything perfect. I want it to go right. But really learning to step back and balance schedule, risk, and cost into that equation. We do not have infinite funds. We also cannot afford failures. And honestly, the biggest heartbreak would be getting almost to the finish line and then not being able to go and pull the trigger and see what happened. And we've got to balance that all the time. If you take too long, if you test too much, if you spend too much, if you have setbacks and you don't run the risk, then maybe you aren't going to get the chance to go there. So it's really learning. It can't be perfect. It's got to be good enough, and you've got to put your risk and manage it where you can.
Yeah, and I'll kind of pull on that one. Good is good enough. We've learned too to balance that with test, right? You got to find that sweet spot where good is good enough, but you want to make sure that you have tested and bounded what you think would be all the failure modes for those different systems. Again, we did that for Peregrine, and we thought we had a good handle on it, and we thought the valve that failed was actually, it had been tested beforehand and worked perfectly fine, and then it failed on orbit, right? So definitely want to do test. Along with the supply chain, I got to keep touching on that though, is we've learned that you need to really do your due diligence when you look at suppliers. And I think it helps once you've selected your supply chain in certain respects for maybe the major subsystems, is to be somewhat embedded with your supplier through development, through testing, ensure that you've got very clear requirements for them to develop, qualify, and test to your specifications. We've also learned that sometimes there's room for interpretation. I'm a big advocate, and this is probably my NASA background, is have explicit requirements and sign up to those ahead of time.
I'm going to take tests a little bit further and say, how do you integrate your testing results with your contingency planning? So circling back to what I kind of talked about earlier, what testing have you completed? What testing are you unable to complete? And how much risk have you brought down versus how much risk still exists in your system? And when you look at that holistic picture, what contingency planning for mission do you need to complete ahead of time? Do you need to have certain software patches ready? Do you have a computer reset procedure already in place? Do your operators know how to recognize the risks when they actually occur? Or do they need to be trained up in that further? So once you start looking at your holistic picture, it's that step. It's you're taking a step back. Your vehicle's built. Maybe it's shipping to the Cape. Maybe it's a little bit earlier than that. What's left? What were you unable to do? And how will that end up showing itself in mission? That's going to be the things that show up in mission, is the things that either you didn't think about or the things you couldn't deal with. So it's all both the known unknowns and the unknown unknowns.
Yeah, I think I mentioned after we landed, it was like no rest for the weary. The real mission starts now, and thankfully this lesson was not learned the hard way, but we had spent a lot of time before the mission preparing for the first couple of hours, the first couple of days on the surface. And that was time well spent. I think everyone was a little surprised by just how much had to happen all at once, right away, as fast as possible. We had 10 NASA payloads on this mission. I think that's the most that's been manifested, and I think CLPS is like, oh, that was a lot. We should maybe rethink that. It certainly was a lot to handle for us as well. And so there was just a lot to do really quick. And also, I mentioned we had the overheating problem from the crater. That put a lot of pressure on getting payload operations done and as those temperatures continue to climb faster than the models predicted. So don't just practice getting there, practice the surface operations as well. And it just goes to really ensure mission success all the way through. Thanks.
All right, so that's going to conclude this panel. I want to thank again the panelists and LSIC for hosting the topic. As several folks kind of alluded to, hopefully future LSICs were able to see a lot of the success stories or the future missions in front of us. So thank you all.
Thank you.